Welcome to the Deep Dive, where we unpack the cutting edge of technology and deliver the insights that truly matter. Today, we're exploring a breakthrough in AI. It promises to teach large language models not just what the right answer is, but why it's right. And, maybe more importantly, how to spot their own logical flaws. Imagine an AI that can truly self-critique, much like a seasoned expert reviewing their own work. That's the kind of game-changing intelligence a new approach called STEPWISER is bringing.
It's a pretty significant shift, isn't it?
Yeah.
Traditionally, when we evaluate an AI, we often just look at the final outcome. Did it get it right or wrong? But as these models tackle increasingly complex multi-step tasks, the path they take to get there, those intermediate steps, they become just as crucial as the final destination itself. This deep dive is really about moving beyond that simple correct or incorrect verdict for the final answer to understanding the underlying logic of each piece of the solution.
Absolutely. So our mission today is to dive into this concept of a generative judge. Think of it less like a simple binary classifier, just giving a thumbs up or thumbs down. It's more like that meticulous teacher who doesn't just mark your math problem wrong, but actually circles the exact line where your algebra went astray and explains why. You'll learn how Stepwiser enhances judgment accuracy, how it improves other LLMs during their training, and maybe the most exciting part, how it empowers models to self-correct in real time. Okay, so let's start with the problem this research is trying to solve. LLMs are incredible these days at taking on complex challenges. They often break them down into multi-step reasoning strategies, things like chain of thought or Cody and React. But even with these advanced techniques, there's a pretty fundamental challenge. If an LLM makes a mistake somewhere along that reasoning path, how do we pinpoint exactly where things went sideways?
That's a really critical point. The core issue is supervising the logical validity of each individual step along the way. Current approaches, often called process reward models or PRMs, they do attempt to provide step-by-step feedback. However, they typically function as black box classifiers. They might assign a score or a label, right? But they don't give you any insight into why they came to that conclusion. You just don't get to see their reasoning process. And sort of compounding that, they rely on these static, human-labeled data sets, which inherently limits their ability to adapt and generalize to new reasoning patterns they haven't encountered before.
Right. So without that explicit rationale, it's really just another black box telling you wrong without offering any real path to improvement. It feels like a pretty significant hurdle if we want AIs to genuinely learn and, evolve their reasoning skills.
Okay, this brings us to where Stepwiser truly innovates. The researchers decided to fundamentally reframe this entire problem. Instead of treating stepwise reward modeling as just a classification task, just labeling a step as good or bad, what was their big conceptual leap? That's where it gets really interesting. They realized that evaluating reasoning steps shouldn't be treated as a simple classification task at all. Not really. Instead, they decided to approach it as a reasoning task in itself.
Oh.
This led them to the concept of a generative judge, an AI that actually reasons about the policy model's reasoning steps. They call this meta-reasoning. The key difference is that before it delivers its final verdict, like good or bad, it outputs what they call thinking tokens. It essentially shows its work. It's a significant paradigm shift, really, towards transparency and a much deeper form of evaluation.
Wow, okay, so it's not just spitting out good or bad, it's actually articulating why it thinks something is good or bad. That feels like a massive game changer for AI transparency, doesn't it? What were the biggest hurdles the team faced in actually getting an AI to, show its work like that?
Indeed. It's about building in that capacity for introspection, for self-analysis. To achieve this, the team focused on three really ingenious components, and each one is critical to making this meta-reasoning actually possible.
Right, so the first of these components tackles a surprisingly fundamental challenge, just defining what an individual step actually is within an LLM's thought process. You might initially think, okay, just split the LLM's output by, say, double line breaks, that should do it. But the paper shows that this often results in these tiny, fragmented, unhelpful segments. It doesn't quite work.
Exactly. And this is where their self-segmentation technique comes in. It's quite clever. Instead of relying on arbitrary breaks like line breaks, they actually train the base LLM to segment its own reasoning into what they call chunks of thought. Now, these aren't just random sentences grouped together. They're designed to be coherent, logically complete units. They accomplish this by prompting a powerful LLM, in this case, Llama 3.170 be it, with a set of specific rules. These rules basically dictate that each chunk must serve a single unified purpose like, say, setting up an equation, performing a specific calculation, or stating a conclusion. Also, all the lines within a chunk must form a continuous, uninterrupted logical flow. and a new chunk only begins when the focus of the reasoning genuinely shifts to a new idea or objective.
Ah, okay. It's kind of like a well-structured math solution, isn't it? You wouldn't want the textual explanation in one step and then the corresponding equation separated into another. You need that whole logical unit together. The paper highlights a great example, actually, where simplifying a complex number, which would normally take like 6 separate fragmented chunks with standard splitting, it becomes a single coherent simplify the second term and formulate equations chunk with this self-segmentation method. It's about capturing the actual logical flow, not just the text formatting.
Precisely. And the practical impact of this is pretty substantial. This self-segmentation significantly reduces the total number of chunks needed. For instance, for a 1.5 billion parameter model, they saw a drop from an average of 9.6 chunks down to just 6.0s. That translates directly into computational savings. It reduced the annotation time required for their data set by about 40%. I mean, that's a saving of weeks on a cluster of 8 A100 GPUs. It makes the whole development process far more efficient and, frankly, more scalable.
Okay, that makes a lot of sense. So with these intelligently segmented thoughts, we now have coherent chunks for the judge to evaluate. But then how do you label these chunks as genuinely good or bad to effectively train your generative judge? That sounds like the next big piece.
Right. So the researchers build upon some existing methods here. They employed Monte Carlo rollouts to estimate something called a Q value for each step. You can think of the Q value as sort of a probability score. From this specific step, how likely is the LLM to successfully reach the final correct answer? A high Q value suggests that step is on a promising path. It's a good move. They run many simulations from that point in the reasoning to get this average success rate.
Okay, so it's like a prediction. How likely are you to succeed if you follow this particular line of reasoning? But I gather they didn't just stop at assigning a simple absolute Q value to each chunk, did they? Because that wouldn't capture the full nuance of making progress.
You're exactly right to point that out. What's truly critical here is that they didn't just look at an absolute measure of quality for a step in isolation. They also thoroughly explored relative methods for assigning these labels, understanding that context, and crucially, progress are key. So, for example, instead of just checking if a step's Q value was positive or not, they also considered things like relative effective reward thresholding. This method looks at the change in the Q value in something called an advantage function. Basically, it rewards steps that actively improve the chances of success, like giving bonus points for genuinely moving forward. And also relative ratio. This looks at the ratio of the Q value after a chunk compared to the Q value before it. If that ratio goes up, it signals progress. If it goes down, it suggests a detrimental step. The key insight here really is that it's not enough to just say a step is correct in isolation. What truly makes an AI judge effective is when it rewards actual progress steps that demonstrably move the model closer to the final solution. These relative signals, which inherently reward forward momentum in the reasoning, consistently produce better performing judges compared to just using an absolute quality measure. It really underscores this idea that progress, not just momentary correctness, is what matters most in complex reasoning.
That makes perfect sense. It's like a good mentor, isn't it? Not just telling you if you're right at this exact moment, but encouraging the actions that lead to genuine improvement down the line.
Okay, so we have these logically segmented chunks, and now we know how to effectively label them based on their contribution to progress. The pieces are almost in place. But how do you actually teach an AI to not just identify a good or bad step, but to explain its reasoning for that judgment? That sounds like the real training challenge, and I guess that's where reinforcement learning comes in.
Precisely. They frame the evaluation itself as a reasoning task using reinforcement learning, or RL. The judge model is trained not just to output a simple label like positive or negative. Crucially, it's trained to first generate its own analytical rationale, its own chain of thought analysis about the correctness of the step it's evaluating. Then, and only then, does it provide the final judgment. This process forces the judge to essentially show its work, providing a much more transparent and, as the results clearly demonstrate, a far more accurate evaluation in the end. Ah, okay. So it's not just a reactive judgment. It's a considered, reasoned opinion based on its own analysis. That's a powerful difference. I also noticed they mentioned doing something pretty clever with their training data to make this all work effectively, right? Because real-world data can often be skewed.
Absolutely. That's a critical detail and one that's often overlooked in these kinds of training processes, prompt data set balancing. See, when these labels, good, bad, are generated automatically using things like Q values, the resulting dataset can be highly imbalanced. For instance, the source notes that for the absolute Q-value method, something like 70% of the samples were initially labeled as correct or positive. Now, if you just train an RL model on such an imbalanced data set, it might just learn a simple trick, default to saying correct most of the time, rather than actually learning to discriminate between good and bad steps. So they address this very carefully by intelligently downsampling the majority class, the positive examples in this case, to ensure a more equal number of positive and negative prompts in the training data. This balancing step is really essential for stable RL training. It prevents the model from becoming overly optimistic and ensures it develops true discriminative ability, the ability to spot both good and bad steps accurately.
That's a crucial detail, yeah. It's about building a judge with a balanced perspective, not just a biased predictor that always leans one way. Okay, so we've walked through the really innovative components of Stepwiser, the intelligent self-segmentation into chunks, the clever relative labeling based on progress, and the RL training for meta-reasoning judge that shows its work. But let's bring it all together. What does this all mean for us? Beyond being a cool technical achievement, how does Stepwiser actually make LLMs smarter, more reliable, and ultimately just better in the real world?
Right. Connecting it to the bigger picture, Stepwiser offers some truly significant practical advantages. First off, it delivers better judgment accuracy. On benchmarks like Process Bench, which are specifically designed to test an LLM's ability to find the very first incorrect step in a reasoning sequence, Stepwiser significantly outperforms traditional discriminative judges and even other RL-trained models. Its ability to meta-reason, to think about the thinking process itself, which it learned through that RL training, seems to be the critical factor here. Second, and this is where it enables a truly powerful capability, it allows for inference-time search, or basically real-time self-correction. Imagine an LLM solving a problem chunk by chunk. After it generates each chunk of thought, Stepwiser evaluates it right then and there. If that chunk is deemed bad or incorrect by the judge, it's immediately discarded. And then the LLM regenerates a new chunk starting from that very same point, trying a different approach. It can even do this multiple times, up to 5 attempts in their setup.
Whoa, that's fascinating. So the AI can actually realize it's making a mistake mid-thought, essentially scrap that line of reasoning, and then try a completely different path all on its own. It's like having a built-in editor constantly checking its work.
Exactly. The paper provides some really compelling examples of this in action. In one math problem, the model's first attempt at generating chunk 3 contained a significant algebraic mistake in applying a formula. Stepwiser caught it, rejected it. Then the model regenerated a second attempt for chunk 3, this time with the correct formula, which ultimately led it to the successful final answer. In another instance, involving a tricky combinatorial balls and boxes problem, the first attempt at chunk 3 made an incorrect adjustment for overcounting possibilities. Again, Stepwiser rejected it, prompting a corrected second attempt that got it right. This chunk reset reasoning, as they call it, allows for continuous self-correction during problem solving. It prevents the model from getting stuck on early errors and propagating them, and consistently leads to higher final accuracy. You can even see evidence of this in the results tables. The rejected length metric shows that Stepwiser models generate more total tokens. Why? Because they're actively discarding flawed reasoning and trying again, which directly demonstrates this superior error detection and correction capability.
That's a profound capability. Really, it means the LLM isn't just blindly pushing forward with a flawed assumption anymore. It's being actively guided, almost coached, by its own internal critic to find the correct logical path. It sounds incredibly effective.
And finally, there's another benefit. It also significantly helps with training data selection. A judge that can accurately assess the quality of individual reasoning steps is invaluable. It can be used to identify higher quality reasoning trajectories from vast amounts of potential training data. These superior trajectories, identified by the Stepwiser judge, can then be used to fine-tune other LLMs. This creates a sort of virtuous cycle. Better judges help create better training data, which in turn leads to other LLMs achieving higher overall performance and reasoning ability. And indeed, the models fine-tuned on data selected by Stepwiser consistently achieve the highest performance compared to the models trained using other data selection methods.
So wrapping up, we've taken quite a deep dive into Stepwiser today. It's a truly innovative approach that teaches LLMs to essentially reason about their own reasoning, from the clever self-segmenting of complex thoughts into digestible chunks, to using reinforcement learning to develop a generative judge that actually explains its verdicts. This system really represents a significant leap forward, a leap towards AI transparency and genuine self-correction. It feels like building a new layer of intelligence within these models.
Absolutely. This ability for an AI not just to solve problems, but to critically evaluate how it solves problems, to
Hmm.
perform a kind of introspection, it truly opens up exciting new avenues. It's really about building more robust, more reliable, and ultimately more genuinely intelligent systems. Systems that can learn from their own internal processes rather than relying solely on external feedback after the fact.
Yeah, what really stands out to me from this deep dive is the idea that the future of truly powerful LLMs might not just be about making them bigger or feeding them more data. It might be just as much about teaching them to be their own best critics, their own internal guides. Imagine an AI that not only knows the answer, but can articulate the exact logical flaw and a million other possible incorrect answers, guiding itself towards true understanding. This deep dive into Stepwiser shows us a clear, practical path towards that incredibly exciting future. Until next time, keep digging, keep learning, and keep questioning.